I think we can talk about getting going. So, good afternoon, everybody. Thanks for giving us your Saturday afternoon. I wanted to just introduce our presenters this afternoon. So our first four lectures were a lot about the organization of the residency and the residents themselves. But part of what's hard about when you can't see a program at a distance is you don't get to meet the dynamic personalities, the people who you would train with. So we have two of our kind of most dynamic personalities today, Albert Kim and Eric Leuthardt. They both have fully functioning labs. They both do clinical work more than any one surgeon could ever be expected to do. And on top of that, they manage to be active in producing plays, writing books, and putting television shows together. So I suspect they both have designed a time machine in their lab so they get 30 or 40 hours out of a day for the amount that they're able to produce. But it's really exciting that they can talk to you a little bit about some of the things that we do at WashU and some of the things that they do in particular that you may not see in other neurosurgery programs. So thanks so much, guys, for being able to talk to us this afternoon.
Yeah, of course, it's my pleasure. Eric, you might be muted.
Sorry, I was muted. My apologies.
Hi, everybody.
Hey, all.
So I don't know, maybe we'll just say a few words about ourselves.
Yeah.
Go ahead first, Eric.
You want me to go first? Okay. All right, so
why not?
So again, hi, my name is Eric Leuthardt. I am as far as just, the title-y stuff, I am a professor of neurosurgery. My clinical practice is mostly brain tumors and epilepsy. I'm also a professor of engineering and the chief of the division of neurotechnology. And that really kind of, encompasses also a center for innovation in neuroscience and technology. But really, I kind of live in the intersection of neurosurgery, which, I like to think is, cutting edge neurosurgery, science, engineering, and business to basically think about how we make new things and bring them to the world.
Great. My name is Albert Kim. I'm an associate professor in neurosurgery, in addition to other departments like neurology, genetics, dev bio. I'm the brain tumor program director, as well as a co-director of the Brain Tumor Center, which is a multidisciplinary center that has medical oncologists, radiation oncologists, and scientists as well. And so on a day-to-day basis, like Eric, I'm doing brain tumor surgeries, but also in the lab. My lab is very molecularly oriented. We've been interested in cell state and mutations, particularly in glioblastoma and other aggressive benign tumors, and doing a lot of work also trying to bring the Brain Tumor Center to even greater heights.
Maybe I should just also just briefly, as far as research, things that I focus on are brain-computer interfaces or thought-controlled devices, and advanced imaging and brain mapping for a number of applications, improved brain mapping for brain tumor surgery, epilepsy surgery, but also for what we call kind of decision analytics, like to help us kind of have better predictions of patient outcomes.
So Eric was like the first person I met when I first came here. I think I met him in the lobby of the Ritz, I think.
I know, I remember that.
And that actually,
we've been buddies ever since.
Yeah, exactly. So we've been doing a lot of different things. Some of it scientific. I think a large part of that is sort of this great. He's focused more on macro systems, neuroscience type things, and I've been more molecular and more micro scale, right? So there are a lot of interfaces for us scientifically, for instance.
I would say we're both kindred spirits in being total geeks, and in that we really enjoy, fundamentally just kind of thinking about all things brain, neuroscience, applications, implications, and that I think, and we've grown together, as surgeons. I think that Albert's taught me a lot. I think I've taught him a little, and then
yeah.
And then, but we've really learned from each other in many different ways. And I think that, one of the fundamental things as far as just philosophically, like succeeding in professionally, it's, having good relationships and having good friends who challenge you to be better. And I think that, Albert and I have, over, the many years now have challenged each other and, prompted us to do things we normally wouldn't do. I think that, and that's, the genesis of us writing plays together. Again, just background, before, I suckered, Albert into joining me into getting involved in these plays. Like, I wrote a couple fiction novels. One's called Red Devil 4, the other's called Limbo, which are all about kind of what the future looks like with neurotechnology. And so Albert and I had to give these community talks, and we were getting really bored with them. And so then finally we decided to kind of partner up and do something more interesting. And that led to kind of a TED Talk style presentation, which then led to kind of people really getting excited about the idea of creating a play. And we wrote the first play, and that was, what was that,
2014, I think, December.
Yeah, that's right. And
6 years ago now.
And actually, funny enough, that got filmed and put out on PBS, and that won an Emmy Award. Mm-hmm. And then we just did our recent one, which took another 4 years to write and put together and raise capital for, and that's actually now nationally syndicated on PBS.
Right.
And so, but I think, one of the things I think we both appreciate, and Albert, please correct me if I'm wrong, but I think doing all the stuff that kind of seems completely not related to neurosurgery, really is. Meaning that I think just prompting creativity, prompting, deeper thinking and larger and bigger thinking, makes you more of a visionary and makes you more adept at having a flexible mind to actually do things that are impactful.
So, absolutely. And, we want to train people, like-minded people who want to change the world. I mean, change the world in neurosurgery maybe, and beyond that. And so I think, that's in the blood of our residency program as well. I mean, sort of these things we talk about, we do, those are the type of people we want to recruit here, really. So I'm just thinking back on 6 years ago when we started that first BrainWorks, and it was a complete random set of circumstances, actually, that it's kind of a funny story. So we were giving these talks, like he was saying, and they were like dry, slideshow lectures about any number of things: brain tumors, how your brain works, how your sympathetic system is activated when you see a cop car and you're speeding, for instance. And then it just so happened that we did it together, and we kind of just bounced things off each other and made fun of him. He made fun of me. I think I had some gear on my head. It was an app that one of your guys in your lab made.
Yeah, right. So we created the first brain-controlled app on the cell phone on the iPhone.
So you put this on your head, and it's reading, I think, from your frontal cortex. You can make a helicopter go up and down basically by thinking about it. It was like an iPhone.
Helicopter.
And so, and then we did that talk, and I guess people responded to it. But this one person, this marketing guy, essentially from Express Scripts, comes out to greet us after to say what a great show. And then the first thing out of his mouth, basically like, "You guys should bring that to Broadway." And I was like, "What are you talking about?"
And most importantly, he caught our attention because he bought us sushi. Like, exactly. That's true when you're a student and a resident and faculty, but we got free food, and that we actually listened to it.
That's absolutely right. And then, and then we wrote the first iteration of BrainWorks, and we had a lot of help. Obviously, it's not just us; it's a lot of buy-in from the hospital, medical center, and the local PBS network, actually. So that was incredibly fun to put together in our busy schedules, obviously.
And then the second one was twice as long. I mean, to give you a sense of, and so we had the second one was a much bigger production. I mean, it was massive. And so I think Albert and I individually had to memorize 100 pages of text cold. And they would correct you over like ands and thes, like if they weren't correctly said in the proper place. And so, and if there's anything that can promote your ability to kind of like memorize things, it's standing in front of 1,000 people, not looking like an idiot. Like that actually was one of the hardest things of my career. Don't you think, Albert? Like,
yeah, no, I agree. It's so easy to get distracted. I mean, we got a lot of help from our kids also. When my daughter actually read lines with us, I mean, I think she probably spent a good, solid 4 days just reading lines with us. And so, that was interesting. But it was very challenging. But, at the same time, I think, especially with the director and some of the other actors involved, I mean, they had a lot of good tips on how to deliver speech in a more dramatic fashion, right? impactful way. And I thought that was also interesting. Yeah.
No,
Anyway, so then I guess that, but we had other reasons to do that. There are educational aspects. So basically the idea behind Brainworks was to just show sort of neuroscience working in the life of an ordinary person, and also sort of what steps they have to go through if they have a disease in the brain.
And also to make neurosurgeons relatable, personal,
yeah,
like
exactly.
that just as kind of Albert and I think share a friendship and a fascination and some just fundamental geekiness about the brain. We wanted to share that enthusiasm with other people and make it not like this dry lecture. And so basically make it a relationship.
Exactly.
And I think I know where you're going with this, but basically that led to kind of our video blog, or not video blog, our podcast,
right,
called Brain Coffee, where basically we just talk about the brain and all random things related to the brain over coffee, which actually, again, we get free donuts, and so which the hospital pays for.
Wonderful coffee, exactly.
Yeah.
And we would talk about random things like like our dogs or Halloween and the neuroscience underlying Halloween, or Santa Claus, or believing in Santa Claus and things like that. And I think that captured a sort of imagination and fascination, honestly, of a lot of people. Yeah.
Yeah, actually, that podcast had the highest traffic of any clinical aspect of the Barnes website. So, so it was, but I think it speaks to, again, the importance of just, kind of being a human being and being relatable.
Yeah, absolutely. Absolutely. I mean, the other cool thing about it was, we did have some other, reasons to do this in addition to education and outreach. We also have, like we said, very active labs. And so we thought this might be a sort of a non-linear way to perhaps get, non-NIH. Eric has a lot of NIH grants. I have 3 NIH grants right now. But often it's not something you can always count on, for instance, especially in the current, era with really high thresholds to get that grant across the finish line. And so you need alternative funding, really, like donations and things like that. So this thankfully also led to a number of donations that have really helped us out.
A very, very large gifts actually that funded our research actually for years. I still have money from the first Brainworks.
Yeah, exactly.
To do high risk things. Basically with grants, you have to keep them very structured, very kind of predictable. Whereas you have it now with some of these philanthropic grants, can do more high risk research, which I think really paid off some dividends.
Exactly. Especially in like the world of molecular biology and cancer. You guys probably know. Well, single cell RNA sequencing first came out in GBM, right? Now it turns out single cell sequencing just for one sample is like $7,000. So you just add up the number of samples, and it's just ridiculous how much just one experiment costs. So things like that could really turbocharge our efforts.
Well, Albert, maybe why don't you just kind of tell everybody just a little bit of that, maybe on a Brainworks or a Brain Coffee level, what you do in your lab.
Oh yeah, okay. So my original interest was in glioblastoma stem cells. So basically, cancer stem cells in glioblastoma. And in glioblastoma, I think there's a lot of evidence now that cancer stem cells exist. I think for a long time, people thought it was a fake thing, like some kind of like Loch Ness monster or something like that. But certainly in the world of GBM, there's abundant evidence, transgenic mice, single cell sequencing in human tumors, and a lot of evidence suggesting that they actually exist. And so we've been interested in how to essentially target glioblastoma stem-like cells. And we've been interested in epigenetics, because the awful truth about GBM is that if you look at 10 GBMs, and this is in a publication that we did with McDonald Genome Institute here, very well known for being part of the TCGA and sequencing a lot of different cancers. We basically found that, well, number one, if you just look at 10 different tumors, like 10 different patients' tumors, the divergence in genetics is crazy. Like everyone has different mutations, number one. Number two, if you look at 2 sectors in each person's tumor, even that is heterogeneous. So like only 50% of the mutations are shared across 2 areas of the same tumor. So it's like astounding the amount of genetic diversity there. So how do you target something, right? So we've been thinking about common mechanisms, and one big common mechanism is this epigenetic mechanism really ruled over by SOX2. SOX2 is a transcription factor that is a pluripotency transcription factor. You guys have probably heard about it, like they're one of the Yamanaka genes, for instance. If you get rid of SOX2 in GBM, which is in every single cell in GBM, then you can't make a tumor anymore. And so we've been really interested in how to control SOX2. That's been sort of one of the major foci in our lab. And, we use different models to study it. We've been using, now we have about 170 human lines that are, basically glioblastoma stem cell cultures. In addition to that, we've been developing a CRISPR-Cas9 system with human embryonic stem cells, which is really cool because then you can have isogenic experiments. You could basically have a much better controlled experiment using those. And at the same time, we've been getting a lot more translational. And this is stuff actually I've been doing with Eric as well. He and I both use a laser extensively for surgery right now. And maybe he can tell you something about how we think about it more even in this pandemic. But I set up a mouse laser basically, and we've been looking at its effects in mice. So it's not just, put the laser in the mouse tumor and kill the tumor. There's a lot of other things going on, turns out. Like the blood-brain barrier is actually opened for about a month after you do laser in humans and in mice. And we're looking at the mechanisms of that and how we can harness that. And then the second thing we're looking at is how the laser, it's different from just like cutting out and taking out all the tumor. You leave the tumor cells there. Potentially the antigens in those tumors are also still there and can be, attacked by your immune system. So we think that microenvironmental impact of lasers is also quite different from craniotomy. So that's some of the stuff we're doing. Yeah. Eric, you wanna?
Yeah, sure.
Please.
Yeah. So, I mean, I guess, I like I said, I have my thumb in a number of different pies. I guess, from a research standpoint, my fundamental kind of the ethos of my lab and my center is really kind of understand how the brain encodes information and figure out applications. And so kind of one of the cornerstone technologies that are brain-computer interfaces, where we basically take signals out of the brain and have people control things with their thoughts. Now, where we initially were working on that, and applying it for spinal cord injury, but the big motor problem or the largest motor deficit from an impact standpoint is stroke. And so really over the last 12 years now, we've been working on developing non-invasive brain-computer interfaces where people use the uninjured side of their brain to control their paralyzed hand after stroke in the chronic stroke setting. And as it turns out that when people do that, you set up a Hebbian model where, again, the idea of things that fire together, wire together. So as they control their paralyzed hand with this robotic exoskeleton that we designed, with the signals coming from the uninjured side of the brain, that their brain's firing and their hand is moving commensurate with their intentions. And that leads to a rewiring of the brain. And so, and then patients, really gain substantive, functional recovery when they should be far beyond the plateau of getting any meaningful function back. And so we've published on that. And, I think, we're looking that hopefully this technology will be, FDA approved and used on patients, within the year. And, but I think that's one of the BCI technologies that we're working on. We're also working on one for chronic pain to remodel, basically using brain-computer interfaces to remodel pathologic circuits. And we're taking that same thinking and also applying that for advanced imaging. So I do a lot with what's called resting state functional MRI, where basically you look at brain networks with MRI, with the MRI scanner. And we used kind of initially similar kind of techniques for understanding these oscillating signals in the MRI scanner. And we looked at basically how to automate brain mapping. So basically you put somebody into a scanner and you get 15 minutes of data. And after developing some analytics, we actually can map what every part of the brain does and have that available for kind of surgical mapping, which was kind of, and that actually, we've used that now here at WashU on 2,000 patients. It's really become the standard of care how we do things. And it's really changed care. And I think another kind of, big thing that I'm interested in, similar to Albert, we've been doing this in many ways together, is that really pushing laser interventions in the brain. And I almost think of it as a kind of, it's an emerging new field, just as you had interventional, vascular, interventional radiology for vascular problems like coiling aneurysms, really becoming a new paradigm for compared to clipping aneurysms. I think we're seeing this emergent field of interventional neuro-oncology, where basically we now are using these hyper minimally invasive approaches of implanting lasers into the brain for treating tumors and epilepsy. And I did the first FDA approved case back in 2010, and we really expanded that a lot here. And then, we do a lot of other neurotech stuff, like my center. We're generating 3 to 5 new medical devices every year. We're starting companies. I think my center's spun out around a total of 8 or 9 companies over the last decade, about one or two every other year. And and just kind of really being involved in the innovation entrepreneur space.
Yeah, and I can't emphasize Eric's ability in what he, bringing something from concept to, person. I can't emphasize how hard that is. And, we have, Eric is a premier, sort of a master at doing that. But I have to tell you, it's so hard to do each of those things. Come up with a concept, proof of concept, just experimentally, get it to a human, get it past regulatory, things like that. It's just very difficult. And that's the sort of stuff Dr. Leuthardt can teach you. So I think that's incredible. Similarly, if you had an idea for a clinical trial, in fact, it's kind of amazing when I first came here a decade ago, how many different things residents were doing in terms of just real science. I'm not talking about like, case series 10 of something. I mean, while those are important, I was just really, really surprised by the depth of the projects of the residents here. And so you could really get involved, get even like a, phase 1, phase 0 trial, or maybe something like, maybe you want to look at sort of biochemical correlates of a trial that's already ongoing. That's super easy to do. And so I think, it's not just like getting papers and stuff like that. I think you could really make a difference with a lot of the things that are going on here scientifically.
I think part of that actually is, one of the things that I think is kind of unique about Washington University is it's got high level intellectual firepower, but it has very Midwestern personality. And the advantage of that is that it's incredibly collaborative. And what that means is, as an example, a resident is really interested in mixing, vascular neurosurgery and functional neurosurgery. And so kind of she came to me, and we've been thinking about novel ways of using vagal nerve stimulation to affect stroke and subarachnoid hemorrhage. And so, I pull in, kind of one of my colleagues who's a biomedical engineer. He's a professor of biomedical engineering. He says, great. I pull in a neurologist, who's a premier expert in stroke. We all kind of talk about this project, and she's kind of leading it. And we're going to be, starting clinical trials in this technology in humans, in the next month. And we're going to be implanting, versions of this technology in mice. And so it's just, you can really, there's a real fluidity with pulling together expertise that I think is unique. That really, I think, gives us an edge in doing cool stuff. And I think it's an advantage for residents. Also, as an example, like I am not a PhD. I have no degree in engineering. I was actually a theology major, and but I wanted to do engineering when I came here as a resident. And so basically, I got into an engineering lab, and kind of my mentor and now my close friend Dan Moran, I learned engineering and built amplifiers and coded and all the other stuff. And now I have a really, really large, robust engineering laboratory. You can learn skills beyond just becoming a neurosurgeon.
Back to that VNS thing, I've been texting that resident, Eric, see
Yeah.
how close she is to set up, because I want to test it out on brain tumors as well. I think it could be cool.
Very close. Very close.
And Eric, he got me to wear one of these VNSs on my ear as well. We've been so I mean, this is not like an isolated thing. This is something that, I love the fact that, we talk about ideas with each other and it spills over into other ideas. I mean, I literally had on this VNS thing because, Eric was convinced that it was helping his memory. So,
actually, it just got published out of UCSF. It helps people learn Mandarin.
Is that right?
Yeah, it's
Only
published.
Mandarin, huh?
Yeah, it does work.
It
And
made me a
actually,
little
if you're studying for your boards, I think I would strongly recommend it.
huh. It made me a little anxious. I remember when I had it
You
on.
know what? I
The other week.
actually, going back on that, it does, because we've actually been doing it now in primates,
Uh-huh.
and it does create a global central activation. So it may amp you up. So for instance, the
Interesting.
reason it helps with depression is because it's amping them up. But if you're at a
I
neutral
see.
setting, it's probably amping you up more, which could promote anxiety. But
I
it
see.
also most certainly, if it's amping you up while you're trying to do a cognitive task, it's going to reinforce that cognitive task.
No, that makes sense. That makes sense. Anyway, yeah, that's just an example of, for instance, of things that we talk about, and we just, um, think about some silly things, but some really interesting things that nobody else is going to put together, honestly. So I think this is sort of what you'll see among a lot of the attendings. I mean, it's not well. Eric and I were good buddies, and probably the BrainWorks thing was kind of unusual because I don't think I've ever been. I don't think I've hung out with somebody so many hours a day for literally like a month. It was like 10 hours a day next to this guy for a month practicing this play. I don't think I've done that since college,
Yeah, right,
like
exactly.
hang out with someone like that. But it's
Without
not
any
just
chemical
us.
supplements, right? Exactly.
Yeah. But we have these sorts of interactions with our other buddies in like for him, engineering school, and us, other tumor specialists like Gavin. I mean, we do a lot of things with Dr. Dunn as well in terms of science and other things. I mean, one good example of that is this Christopher Davidson forum that donation, that BrainWorks donation that Eric mentioned, that set up not only our labs, but it also set up this forum of experts that we hold on a every 2-year basis. And so you guys probably heard about the CNS tumor section, right? And AANS CNS tumor section. So that's every other year, the major satellite meeting. And so what we did was in between every other year, complementing them. We have this forum, Christopher Davidson Forum, where we invite like-minded individuals. So basically, tumor surgeons out there with labs or thinking about science, and they come into St. Louis, and we have like a think tank basically for 2 days, and we have some great speakers come in. Like we had the NINDS director, Koroshet's come in last time. We had one of Eric's buddies who's actually probably working on one of the vaccines, right?
Yeah, he's the CEO of Inovio.
Yeah,
If you've heard
what
of
a
Inovio.
great guy. What a nice
Yeah.
guy. He was fun to hang out with. He was speaking. And then we had Mario Suva, right? The father of single cell RNA-seq in GBM come and give a nice talk on cell state. And so that's just 1 year. We've already held this thing 3 times. And so that's one of the things like sort of we do together, we do with each other, and it's at a really high level. And, honestly, the reason we did it was like, we just wanted to make a meeting where we wanted to attend, I mean, there's so many meetings to go to, and you're like, this is getting boring. This is not really interesting. So we're just going to make a meeting where we just want to go to it. And then
Just talk to the most impressive people in the fields that we're interested in.
Exactly. And so it was a high level. It was fun. A lot of networking and collaborations have come out of that. So
Yeah.
So there's a lot of cross fertilization, I guess, is what I'm saying in the department.
Oh, do you guys want to ask us any questions? So we're just not blathering.
Sure. Drs. Kim and Dr. Leuthardt, thank you for taking the time to speak with us today. Everything is really cool and exciting. I'm curious what advice you have for students who are interested in becoming physician scientists who would also like to take things to trial or take things translationally. Like you take so many, it sounds like you take so many products to trial. Like do you just have a ton of irons in the fire, or how do you go about doing that?
I think it's this, you're iteratively ramping up. Like and I got some really wonderful advice from my chairman when I was kind of at your stage or just starting my residency. And I think the key is first, well, I think there's 2 things. One, I can do a lot of irons in the fire because, I've kind of built up infrastructure to really help me parallel process a lot of stuff. But when you first start, I think it's key to become really, really good at one thing that allows you to stand out. Right. And then you basically what I call collateralize that, so for instance, I first became, I had my first hit as a resident. I created one of the first human brain computer interface platforms, getting on 20 years ago now. And then basically I took those same techniques and started to apply it to brain mapping, with electrophysiology. Then I took those same techniques and applied it to functional MRI. And then I've now been starting to play with what we call liquid biopsy, like using ultrasound on the brain to do interesting things with MRI. But I didn't get one, really, big hit where you go deep and become an expert on something. To complement that, like, so that you don't, go deep on something that's completely worthless, is I think it's important early in your career to really, really think deeply about the future. And not just the classic, like, I'm at an interview, so what do you want to do in 10 years type of future? What does the future look like? Really push yourself hard to imagine a future beyond kind of what you're experiencing now. And then think about, what kind of role you want to have in that future. And then think about this, then you work your way backwards to the steps. And this is where you go deep on the developing a deep expertise on that first step that points you towards that trajectory. Kind of as an example, when I first started residency, even though I didn't know dingus about like anything, like, I really wanted to make brain computer interfaces and this idea of neuroprosthetics a reality. I thought that was the future of neurosurgery. And back then it was completely, there was just a few, getting around 99, 2000, there was just a few demonstrations of this in primates. And so I really, took time to say, okay, I really want to do this. I really think BCI, brain computer interfaces, are important. How do I do that? Well, I have to get some experience and knowledge and know-how in engineering. I have to partner with an engineer to figure out how to do some early steps and, really become expert at this, and then bring this to the field of neurosurgery. And so kind of, when I started doing my research, I published the first paper of doing a human invasive BCI with ECOG, or electrocorticography, using epilepsy patients. And that was a big hit. And then it supported the longer term vision, which we've been iteratively working on ever since. But I think, have a big vision, and that's okay. I mean, you don't have to be bashful about it. And then think about the very concrete steps. Even if it's, 0.001% in the direction of that big vision, it validates that vision. And so I think that would be, think big and then go deep and narrow for a step towards that big idea. So that'd be my advice. Albert, what are your thoughts?
I completely agree with that. I mean, you really need, so the vision is very important, but you really need to focus on something that you have deep expertise in. I mean, there's so many people these days who are just kind of good at a lot of different things. I think it's really important that you become an expert along that, whether it's the first step or it's a domain or a certain technology approach. You need deep expertise in that. That's really going to help you, honestly, just sort of for your career happiness, but also to help you get your first job.
Yeah.
I think that's great advice. I came at it from a little different angle from Eric. I came from developmental biology. So I have a PhD. I studied AKT when I was a grad student, when AKT was just discovered, which is kind of a crazy thing. Now AKT is everywhere. Super competitive field though at that time. And then I studied dendritic morphogenesis. So just basically how dendrites form and how circuits are made at the molecular level with Azad Bani, who was the chair of neuroscience here. So I came at GBM from a developmental angle. And it was kind of like someone splashing like cold water on my face. So when I went into GBM, cancers are just so much more complicated than development. But I certainly did leverage sort of the techniques, technology, and the concepts in development for me to learn about GBM. Now, I think for GBM, I mean, what is the vision there? I mean, at some level, we have to do better than just the surgery. I mean, we have so many surgeons, including me, who pat ourselves on the back after we do gross total resection of a GBM, and then like inevitably 6 months later, they're dying and they're all dead, right? We have to do better than this. And so, I think we just have to, there's a basic sort of lack of knowledge about the essential biology of GBM. We can't just throw stuff, you don't just throw stuff on your enemy before you understand the enemy, right? So I think we just need fundamentally more basic knowledge. Like we don't even know how the immune system works, for instance, in the brain, is one huge gaping hole in our knowledge. And then, you know, the other thing to think about, at least if you're a brain tumor surgeon, is really to do more science while you're doing the surgery. Now that might mean like taking, you know, different parts of the tumor and studying different parts. For instance, we become more interested in the edge because, you know, quite honestly, we cut it all out except the edge, and then the edge comes back. So we should understand edge biology much better, for instance. And, you know, just really thinking deeply about, you know, in addition to just cutting out the tumor, and, you know, you have to be a good surgeon. For sure, we teach you how to be a good surgeon here. You have to be an authentic and skillful surgeon. But, you know, really push yourself to think, how can I be doing science more while I'm cutting this out? So that's what we're actively thinking about. And, you know, that sometimes it's small steps, again, like tissue. Other times, you know, now we're using 5-ALA more. I got Eric to use it the other day. Actually, in that case,
I really like it now.
Yeah, it's really cool. So the 5-ALA, you can see it labels tumor cells, as you guys probably know or will learn, because of because of transporters and also because of a deficiency in ferroketolase, I think, in tumor cells. So it lights up like lava, basically. But you can study different areas of the tumor that way. I mean, some parts are obviously lava pink, right? But then there are also areas in the infiltrative margin, for instance, that you might be able to FACS sort those cells out of, and then you could study those cells, which are probably really more relevant for recurrence. But like for Eric's case, I think Eric's like, I asked him if I could take a sample, and he's like, no, just scrub in. And so I scrub in to his case. I take a melon ball piece of tumor from 2 different edge areas, and then, you know, I basically ran that back to the lab, and then did OCT, got that ready. We'll be doing some interesting things with that. So now, thanks for that sample.
But I'd highlight one thing that Albert says is that, you know, you need to leverage the unique ability as a neurosurgeon to have access to humans and human brains, which all the other neuroscientists don't, right? Like they're working with primates or they're working with mice. But if you can really utilize, and as the division chief of neurotechnology, one thing I feel passionate about is that every patient should generate data that can inform further technology development, inform further scientific applications, and inform further translation. So, you know, whether it's, you know, so sometimes, you know, like sometimes I do these big resections either for epilepsy or for tumors. Kind of as an example, you know, I gave a bunch of tissue to Albert. Sometimes we have to take normal tissue. So I'll take out, you know, I'll take that normal tissue and I'll give it to some of the fundamental biologists so we can look at, you know, cellular mechanisms and cellular wiring of cortex. And that gives us a really unique edge in understanding the brain.
Yeah. This is I think one of the guys he's talking about is this guy Keith Hengen, who's he's fantastic, phenomenal systems neuroscientist, and yeah. So we've been talking to him about he's interested in how the brain processes information and sort of the fidelity of information, and so he's been using samples that we've been giving him. That's been really cool. I agree, but somehow doing science with the surgery more, if you're a tumor surgeon, I think is a really important aspect of it. I mean, microsurgery is extremely important still. I mean, I love the microscope. I use a mouthpiece, and, you know, you have to be good. But we have to do more than just cut the thing out, especially if we're going to make a real difference. Yeah, I agree with that.
Thank you so much for the advice. And I love the philosophy that every patient should generate data. That's fantastic.
Yeah. I mean, exactly. We got to care for that person, but then also change the future with that person. Yeah, exactly.
What else? Anybody else have any questions?
I've got a question. Hey, thanks for doing this. I'm curious, like for students who have an interest in potentially doing some of these basic and translational type projects, but who didn't do something like a PhD, what kind of advice would you have for, I guess during like junior residency, sort of building up the skills necessary and making the relationships while you're a junior resident, such that you can get the most out of your researchers when you start to really focus.
Maybe I can field that one. Because again, I don't have a PhD, but now I've actually trained nearly 24 PhDs. So I think the key is actually early on in the moment you arrive, actually think very deeply about, you know, if you can get a sense of where you want to go, whether you want to be a brain tumor surgeon, whether you want to be this type of surgeon, or just even more general, like what field, like, and if you can find a technical or a scientific mentor early on. So for me, it was this guy, Dan Moran. And again, he's, he was my mentor as a resident, but close friend now. We have many grants together as co-PIs. But basically where in addition to, just training as a resident, you're developing a relationship with that mentor. You're developing, knowledge and know-how with that mentor. And even if it's just, you're just doing a little bit of stuff with that individual as you're moving along, so that when you hit the ground, that you've already planned your research project. You already started writing grants for your research project. You've already done literature searches. You've become knowledgeable. So that when you do your research during that time, that you hit the ground running and you develop, more competence and capability. And all you really need is one big important paper, and then you're on your way. And then, you start to, like, you become, faculty member. And if you have, a joint appointment with whatever, school or department that is outside of neurosurgery, for me, it's engineering. You start having engineering students, or, start having PhDs, and they end up teaching you as much as you teach them. And then you just kind of grow. And it's because I think fundamentally, I'm sorry, I'm going to get on a little bit of a high horse here, is that we kind of always assume, training as a physician, or that you need to have a degree or formal training for every little thing that you do. And for certain things like neurosurgery, that's true. For a lot of other stuff, you just have to have a mind towards learning and becoming expert at it, in a self-volitional way. And you can do it. And I think for science and engineering, that's absolutely true. So anyway, but like, you don't have to feel like you have a PhD to become a good scientist, for instance.
I mean, I would say our chair is also a great example of this, right? Greg Zipfel is a MD, didn't get a PhD. He's running a thriving lab that's NIH funded. And some of the keys is, some programmatic things are in place to help you achieve that, right? So we have 1.5 years for most people, but there's also a 2-year slot, which we're actually thinking about expanding, but that's an ongoing discussion. But right now, out of the 3 people every year, one of those people is getting 2 years, the other 2 is getting 1.5 years. And so that certainly helps. People like Eric, people like Dr. Zipfel, they're really, it's great evidence of the fact that you can do it. A lot of it is also cultural, right? Some departments are just going to think this is ridiculous and not worthy of your time, and we are just the opposite of that. We think that this is the way to change the field. And so a lot of it is culture. It's top down.
Yeah, I think that's right.
Can you guys talk about what you feel like the appropriate balance of research and clinical training is? I think a lot of us are interested in programs like WashU because of the emphasis they place on research and the amount of time that they give us, projected time that they give us for research. But at least for me, one kind of concern that I have is that, if I spend 2 years working in a basic science lab, that's two less years that I'm spending with patients, and 2 less years that I'm spending, working in the operating room and working in the ICU. Do you guys feel like, at least for your residents, do you ever see them sort of struggling or having any kind of challenges in returning to the clinical years and kind of brushing up with those skills after doing research?
Absolutely not.
Yeah, not even a little. You know what it is? I think they're actually even better when they come back, right? A lot of them, as if they've integrated the information better. And I can tell you, I did 2 years of research. Sure, the first week, maybe it's slightly rough. Actually, mostly because you don't remember the names of the instruments. Your hands know what to do, but you don't remember like it's an Adson or something. But honestly, it comes back very quickly. And I don't think you're diminished at all as a neurosurgeon. And there's so much variability in surgical ability also. And I think it's really comes down to the same thing Eric was talking about before. It's self-motivated, volitional pursuit of excellence and knowledge. Like, I don't know anyone who's a bad surgeon who literally goes, falls asleep reading like, Rotens every night. I don't know anyone who knows his or her skull base anatomy cold, who is a bad surgeon. I just haven't met that kind of person yet. So it's really, again, just your own self-motivation.
Yeah. And I think also kind of to further complement that, I think one of the things that we do is that we send people to Ireland for 6 months. And there, you know, when you're on call, you're the only operative neurosurgeon for the nation of Ireland. So, and so you're busy and you are on your own during that period of time. And so when you're coming back as a chief, you're not learning how to, like, you know, take out a subdural. You're now at a level where you can operate independently. You're now refining your skills, you know, to master class type of stuff.
And finally, maybe to your point again, Dr. Zipfel, who is a wonderful surgeon. I mean, he is really a master surgeon. He took 2 years off, and that's where I met Dr. Zipfel. Actually, I met him here. We were in the same lab, and he took 2 years off, and I think he did just fine. Yeah.
I got one more question for you. Thank you both again so much for doing this. This has been fantastic. I think hearing about all these great successes you guys have had and working on such innovative things, such new ideas, I imagine along the way there were probably some obstacles that you've had to overcome. So I was wondering if you could speak a little bit to the challenges that you guys have seen on this route in these journeys to obviously become the experts that you are and this great advice that you've given us. I'm wondering if you guys could talk a little bit about some of the harder parts of that journey.
It's a good question. I mean, you know, when I give talks about, you know, innovation or, you know, science, I mean, actually, you know, the notion of failure is actually a really important one, meaning that many times, you know, in the medical world, you know, we see a failure as, you know, something that is truly adverse and negative, meaning certainly errors in care, you know, we are held to a high standard. We can't have that. But errors and everything else, like, you know, that's just, you know, kind of, if you see it as a learning opportunity, then it makes you better. And I'll give you a concrete example of that. So part of the reason that I got involved with laser surgery when I did is we were working pretty hard in my center to create a minimally invasive technology for tumor resections. And it was called the Tumor Resection Device, or TRD, or TURD. And I can't tell you how many sheep, lamb brains we went through trying to, you know, we had this kind of, you know, kind of look like a, I don't know, this like wire cage electrocautery type of thing. And it just—
Love the name, by the way, Eric.
What's that?
Love the name.
The name was appropriate because it failed miserably. And, you know, we put a lot of time into that. We put a lot of effort into that. And it just couldn't seem to get it right. And but that exercise of wanting to make a minimally invasive device primed me for when the solution did come along, which was the laser. That I was like, oh, this is what we got to do. And I don't think if I would have gone through that failure experience, that I would have been as primed to see the solution and its importance for the future going forward. And so I think that, you know, is just, if you're not failing, then you're actually not taking enough risks to propel yourself forward. So I think, you know, actually pushing yourself to error scientifically and where error is okay is really important for if you're going to, you know, push the edge of stuff. I mean, those are my initial thoughts.
Yeah, no, that's absolutely right. I mean, that is a great lesson for sure. I'm just thinking about some other things I thought about along the way, especially in the first 5 years. And time management is probably one of the biggest hurdles.
Good one. Yep. Yeah, that's a good point.
I would say even, I mean, to this day, obviously, because now we're doing more and more things that we need to delegate. But, you know, in the first 5 years, it's difficult to balance it at the beginning, quite honestly. And it's great having colleagues like Eric, who was, you know, several years ahead of me when I first came here, and I could get advice from him. In fact, I got a lot of advice from Dr. Zipfel as well, because they both had made it, you know, in a real way. NIH funding, great surgeons, doing innovative things. So getting advice about time management probably was the most important thing at the beginning, because quite honestly, there are times, I mean, it's not unique to me or anybody. There are times like you think you're not gonna have a lab anymore, right? You have NIH funding, you've gotten rejected again by the NIH for your R grant, for instance, and you just have to do it again and again. And so just learning that perseverance is important, learning to manage your time.
I think, yeah, perseverance for sure. Because again, I think we all go through this phase of like, year 2, 3, and 4, where you just get, you were like it just rejected so much, right? It's just, and I always want to keep that list of all those reviewer rejections for all the things that I thought was important. And you just have to push through it and not take it personally and, dust yourself off. I just remember when I was first writing grants, it would take months to put these things together, and you have so much emotional energy invested, and then just not even, and you just gotta, do it again and again and again, and eventually you make it through. And then once you make it through, you're considered legit, and then each time it gets easier, and you have to push through that.
If you have a reasonable idea, I think most of the failures are actually from lack of perseverance. That sounds like it sounds like an after-school special or something like that, but that's true. It's just that a lot of people, a lot of nurses, we're busy, right? And so if you just don't prioritize that and you don't put the grant in the number of times you need it to get it over the finish line, you're just not going to get it. So I think a lot of it is just persistence, reasonable idea and persistence. And it certainly helps, again, to have colleagues who are in the same boat. And so getting advice from them,
and sometimes
maybe commiserating.
Yeah. Well, I think a quote I've used before is like, failure is common, success is inevitable, right? But that means you got to be persistent.
Yeah. Keep plugging at it. Exactly. That's probably the biggest lesson I learned.
That's terrific insight. Thank you both so much. I appreciate it.
Thanks, guys, for coming to talk to us today. I'm just curious, could you give us an example of something that kind of over the course of your career, like really surprised you or just kind of hit you in the face and it ended up really working out when you didn't really expect it to?
There are a lot of things
scientifically or clinically or personally, or what do you think?
Anything you guys think.
Something I didn't expect, but then ended up working out.
I've got one, the IPSI hand for me was one of those.
This is the BCI he was talking about for chronic stroke.
So I'll give you an example. Like one, so when we were first studying brain-computer interfaces, the initial inclination was always to use the kind of normal motor cortex to control contralateral movements for the purposes of spinal cord injury, right? And I remember back in 2006, we always had this kind of, this really thorough motor task where basically, somebody would have electrodes in their brain and they would do kind of, the right hand movements, left hand movements, both movements. And one of the things, and my graduate student says, I'm getting all these inappropriate findings. Anytime somebody moves their ipsilateral limb, we're seeing activations. And at that time, back in the early 2000s, the notion of what we call ipsilateral motor processing, that there's motor signals associated with same-sided limb movements, just didn't exist. And so, and we thought we were totally screwing up our paradigm, or that the recordings were wrong, or the electrodes were, misconnected. But we kind of, stuck with it and kept on doing it. We actually ended up proving out that there was a ipsilateral motor cortical physiology, and suddenly that opened all the vista doors for suddenly that we could use that physiology for a brain-computer interface for stroke, because it was always assumed that you couldn't do a brain-computer interface to restore motor function in stroke because motor cortex is lost, right? You only have contralateral movements or contralateral intentions. And so that, in a lot of, I think, great science doesn't happen with aha, but usually somebody's saying, oh, that's funny. You know what I mean? And then you kind of dive deeper down into it.
Yeah, actually, you reminded me of another example. I was going to say laser when I got here, because Eric had just done the first FDA approved laser. I got there maybe just under a year later. Yeah. And one of our master strategies, this is also thanks to our previous chairman, was to have me trained up under Eric on laser. But then when I saw him first doing the laser and I just looked at the scans of these patients, brain tumor patients, I was like, that's crazy. I was like, why are you doing that? Why don't you just cut it out? What are you doing? And so fast forward just a couple of years, and now I'm like one of the biggest advocates, and we do our 300th case recently. I didn't think it was going to go with that, because I came out of a skull-based fellowship, right? I wanted to fillet people's heads open and cut the bone out and and really have my hands close to the tumor and, you know, cell by cell dissect them out. That was how I was trained. So when I saw Eric doing that with a laser, I was like, wow, this is nuts. But, you know, I have to say, I think it's the go-to therapy now for certain diseases like recurrent glioblastoma, low-grade gliomas. You really got me convinced on that one. We do meningiomas with it sometimes now. And so that's something that definitely, I didn't expect that to be so, really change the way I look at everything. So that was pretty interesting.
One thing I you know, that, and this is, I think, you know, why Albert is, you know, kind of such an unbelievable success is that Albert always has an open mind. Like, you know, he will say, I think that's crazy, but you know, he will give, you know, whatever it is, some consideration. I'll be like, Albert, I think we should do a play. He's like, that's crazy. But you know what?
That was crazy.
that was crazy, but like, but it was still worth it. But, or, you know, but he really maintains an open mind, you know, to kind of, you know, divergent opinions. And I think that is it's just a case, you know, like being very open-minded to different perspectives, and not just kind of saying, you know, this is the way we do it, or becoming dogmatic about your way of doing things or your way of thinking about things, is, I think, what allows you to evolve as a person, physician, and surgeon.
Yeah, and it's really easy to be dogmatic in neurosurgery. I'm sure you guys have seen that. You know, strong opinions about everything, right? So it is important to keep an open mind. The other thing I was going to say real briefly in terms of something that changed my mind about how I'm looking at something is a scientific thing. I had an NRSA fellowship in my postdoc during my residency for glioblastoma, basically. But then about 2 months into it, I did some Western blot looking at neurons for a certain protein that shouldn't have existed there. So then I look at this blot. It's not glioblastoma, it's postmitotic neurons. There's a protein there that shouldn't be there. And then I show it to my boss, who was Azad at the time. And we both look at each other and we're like, we're not studying GBM anymore. Forget it. Like, we completely dropped it. And then a year later, we had a cell paper on dendrite morphogenesis by this mitotic regulator. And that led to an R01 for him, like Cell Science, Nature Neuroscience paper, GND paper, like all because of that one stupid blot, that Western blot. So, you know, you really have to just follow where the data leads you and just follow your passion. Yeah.
You know, and be willing to kill your own sacred cows. You know,
yeah.
I think that's, you know, like for me, and just, you know, my first company that I started, we were initially creating, you know, invasive brain-computer interfaces for spinal cord injury, but as this emerging understanding of ipsilateral motor physiology and that we could detect it non-invasively, we suddenly, you know, we had to basically say, okay, we're going to completely change to address this larger patient population in a non-invasive way. And it really required, you know, again, I was known back then as the ECOG scientist, ECOG BCI guy, but I had to, you know, put that aside to push brain-computer interfaces forward. So yeah, you got to just take it in the direction that it is, you know, the biggest opportunity.
You know, I did want to, because I think Eric's very humble about himself. I mean, one thing he didn't plug, I think, even sufficiently enough, was this resting state research that he said he's doing. That, you know, he said he's done 2,000 resting state images in the patients. So I got to tell you, I personally use the resting state algorithm that he designed for my patients. Everybody in the department does. And so when I get, you know, my laser patient for next week, that person's going to get resting state imaging, and I'm going to see how close that lesion is to language, for instance. And on the basis of that preoperative imaging, I'm going to decide, you know, whether or not laser is a good idea, or, you know, or awake craniotomy. And so that's really changed our practice. So that's something that's not in the research realm only anymore. It's something clinically active, and that we've been doing honestly for like a decade now, right?
Yeah. Yeah.
So
I mean, I think that, you know, I really feel strongly about like the scientific findings that, you know, that I want to basically make them translate to people, you know, and make them real. And that involves starting companies and clinically trialing it and using it, and really pushing the envelope on that. And that's important to me. And
yeah, the person who did that in his lab is now a resident with us now. So the person who built the algorithm for clinical resting state is one of our residents right now.
Yeah, no, it's cool.
That's awesome.
Well, guys, I'm going to say thank you for giving us your Sunday. I think this was a great talk. It was a nice break from the format of what we've had. And thank you to all the students who have turned in for the talk today and asked such great questions. We really appreciate your showing interest in us, and we hope that you can take something useful away from these lectures. We're going to be back on Sunday next week. Next week, we're going to do a series of complex cases. So we're going to have a spine surgeon, we're going to have a vascular surgeon, and we're going to have a tumor surgeon, and we're going to have a pediatric neurosurgeon, all kind of showing some unusual cases that we treat here at WashU. And then we'll have one final lecture the week after from a collection of people who have funded our R1 labs. So we appreciate your time, and again, we're going to be back on Sunday next week. Thanks so much for joining to us.
Great. Thanks, everyone.
Thanks for listening in.
Nice meeting you, folks. See you.